Hi, so I'm Ivan. I'm going to talk about Quantile multi-arm bandit with 1-bit feedback. This is joint work with my supervisor, Scarlett. We are from the National University of Singapore. Okay, so we first quickly review the vanilla setting of best arm identification. So the model is pretty simple. You have k arms, and each of them has some mean rewards, mu1 to mu_k. And the learner's goal is to identify the best arm, in this case, the one with the highest mean, with high probability, using as few samplings or arm pools as possible. And we know there's this upper bound on the achievability, which is given by this gap square, where the gap is defined as the difference of arm mean. So there are a few potential issues with this model in terms of applications. So for example, mean may not always be the ideal performance measure. So for example, if let's say you are given these two investment portfolios, yes, the second one will have a highest average outcome. You probably will get 9 million. The first one you get 1 million. But then, I don't know, I would be very worried if someone sell the second investment portfolio to me. And another issue is typically in the setting for best arm identification, the learner needs the precise observation or realization of the rewards. But in a lot of applications, this is not a very realistic setting because the uplink communication from the sensor to the server or learner can be very restrictive due to the uplink communication bandwidth. And I now introduce our problem setup. So firstly, instead of defining the best arm as the one with the highest mean, we define it as the highest quantile for some q between 0 and 1. For example, if q is 0, you are just defining as the best worst case scenario. And q equal to 0.5 is just the best median. And we assume that the quantile is bounded between 0 and lambda. The lambda is just the interval, length of the interval, and 0 is just, without loss of generality, assume is 0 to lambda. And for the second issue, the one about the communication constraint, we have this setup where at each round, the learner decides an arm to be pooled, and then tells that to some agent, but at the same time, sends some side information to the agent. And now the agent will pull the arm, observe the reward, and report back to the learner. But there is one huge restriction in the message from the agent to the learner. The size of the message has to be 1 bit. And the goal is similar to before. We want to be able to find an optimal arm with high probability, but we have epsilon relaxation here. And as before, we want to use as few sampling or as few arm pool as possible. So we have an algorithm that is based on active elimination for those who know. It's pretty strict. The idea is pretty simple. So let's say you want to learn the medians of all the arms. You just build confidence intervals of each arm. So let's say the median is bounded between the so-called LCB, lower confidence bound, and the upper confidence bound. And let's say, for example, you have 2 arms, and then you observe the UCB of the first arm is less than equal to the LCB of second arm. You can safely eliminate arm 1. And you can terminate when you have found an arm that is good enough. So that's the idea of elimination. So the problem is, with this communication constraint, it may be tricky to compute the lower confidence bound and upper confidence bound. So for example, for the mean-based setting, the LCB and UCB are defined based on the empirical average. And here you can probably think, maybe you just use some empirical quantile. But then if you look at the setup, it's not immediately obvious how we can compute the empirical quantile just from the 1-bit message. So to overcome this issue, we use noisy binary search technique. So in the site information, the learner send a thresholding query to the agent. And then now the agent just answer yes, no. And from this 1-bit comparison feedback, the learner will use noisy binary search technique on the 0 to lambda to compute the associated LCB and UCD. And this noisy binary search step, compared to directly using empirical quantile, will just cause a multiplicative factor of log lambda or epsilon, as we will see later in the upper bound. Now that we have described the algorithm, we would like to know the upper bound. But before telling you the upper bound, we need to tell you about the arm gap. So in the mean-based setting, it's pretty straightforward. It's just the difference of arm means. But for the quantile, we have to be a bit more careful. So we differentiate between the cases for those that are good arms and the bad arms. So the first category is a bad arm. So essentially, we are just looking at the weight on how much you can transfer between distribution. So imagine, let's say, this is a very large number, let's say near to 0.5. That means it's very easy to distinguish, to identify this is a bad arm. But when it's very small, that means you have to pull a lot of arm to be able to confidently tell that this arm is suboptimal. And for the good arms, they just define on the opposite direction. So we just say how much better compared to the other arms. So for example, let's say you can afford to put a big delta here. Like let's say the extreme case 0.5, that means even your worst case arm is better than the other arms. And from this arm gap, we first have a solvability theorem. It says, let's say you have a fixed instance of arms, and you look at all their arm gaps. If their biggest gap is straightly larger than 0, then this instance is solvable by the algorithm we described earlier. Conversely, if the biggest gap is 0, this instance is actually not solvable by any PEG algorithm, where PEG is similarly defined in earlier talks, in earlier session. Okay, now we look at our upper bound. So with high probability, the algorithm can return an epsilon optimum when it's possible. And the number of output or sample is bounded by these terms here. So for those who have seen the mean-based bandit, you can see that the first two terms are kind of identical. And the last term is basically the cost of binary search. Conversely, we have a worst-case lower bound that shows that any PEG guarantee algorithm will need at least this number of arm pools. So we can see that they are kind of matching up to these two terms. And interestingly, the lower bound holds even in the absence of the 1-bit constraint. So that means these lower bounds will hold even if you remove the communication constraint channel. And so what does that tell us is that at least for the problem of, let's say, Quantile bandit, adding this extra 1-bit constraint doesn't affect the complexity much. So to conclude, we study a variant of best arm identification with two extra elements. The first one being, instead of best arm defined by mean, we use Quantile, and then we have the 1-bit communication constraint feedback. And our algorithm is based on elimination technique and noisy binary search. And we managed to obtain matching upper and instance upper bound and worst case lower bound. And the lower bound tells us that the 1-bit constraint does not impact the complexity much. That's all I want to talk for today. Thank you.
incredibly good time management too.
Thanks.
We have time for questions.
Yes.
Thanks for the interesting talk. So just to confirm, there's no limitation on the channel between the learner and the agent, right, in that direction?
So the downlink, right? Like from here, the site information?
Yeah. Do you have any constraints
yes,
on that?
So in the setup, there's no restriction on how big the message can be. Even though for our algorithm, the idea is that for the interval 0 to lambda, you kind of discretize them into, let's say, endpoints, and then you tell them specific points. So actually, in our algorithm, it doesn't require a lot of, the size is not that big, but then, yes, in the setup, there's no restriction.
Okay, thank you.
Any other questions?
Yes. Thanks for the interesting talk. Can the learner query about information, some sampling that happened in the past? Like at TH round, can the learner ask, is xt minus 1 less than equal to something?
So like the reward observed in previous round, right?
Yeah.
In our setup, no. The
Okay.
agent is memoryless.
Okay, that's what my question was.
Yes, about this channel, I guess what I'm wondering is this also something that appears in the lower bound as well? Like in the lower bound, the learner is still allowed to ask questions to the agent, or?
Okay. So the question is whether the lower bound involves this communication channel. Is no. So the lower bound actually holds for the problem without this thing. So imagine the learner actually get to observe the precise realization or the observation, and that lower bound still holds. Yeah, so maybe it's interesting to see whether we can tighten the lower bound. Let's say because there's this term. Intuitively, it feels like it's kind of necessary to locate when you have this 1-bit constraint, but surprisingly, it's kind of surprisingly hard to show this for a general 1-bit channel. So let's say if you restrict it to thresholding query instead of any 1-bit question, sorry, any 1-bit feedback, then you can show that this is necessary just by straightforward argument of, like how, let's say you have n equals to log over epsilon option, then you need log of this amount by basic information theoretic argument. But then for a very general 1-bit message, we haven't found a way to show that it's necessary.
And also we have this characterization in the previous slide, I guess. We said that if delta k is 0, then the instance is unsolvable. But can you elaborate on what it means that this is unsolvable? Like, is it impossible to figure out what is the best median?
So unsolvable because the thing is you need to be packed. So that means any instance that satisfy, let's say, all median within 0 to lambda, you have to be able to solve them. So when, let's say, delta is 0, you can kind of create 2 arbitrary closed instances where the set of satisfying arm does not intersect. And then you show that, let's say, for sake of contradiction, the first one, the algorithm can be able to find the good arm. Then the second one will definitely fail because they are too close to each other. Yeah, so that's the idea.
Yeah, but does this not mean that this is unsolvable in sort of like an uninteresting way that?
Do you mean what?
Like I mean that. So it doesn't really matter which one of these 2 actions you output at the end. Maybe you still want to characterize the hardness of telling these 2 apart from all the other ones.
That's good. No, I'm pretty sure there are examples where, let's say, when delta is 0, but then it's clear that, let's say, 1 is there's this good arm, but then no algorithm will be able to figure out. Because, so that's the tricky thing about Quantile, you can make them arbitrarily flat apart, and then so that the algorithm it's hard for the algorithm to decide whether, let's say, this is a good arm or bad arm. So that's the idea why it can be hard.